This video will cover the Fischer esterification reaction. This reaction involves the synthesis of esters using alcohols and carboxylic acids. Mixing an alcohol and a carboxylic acid in the presence of sulfuric acid and heat produces the ester and water. Let's look at this mechanism. The alcohol is our nucleophile and the carboxylic acid is our electrophile. The first step of this mechanism will involve protonation of the electrophile with the strong acid to produce a better electrophile. Notice that the electrophile has two groups that could potentially be protonated, the hydroxyl oxygen and the carbonyl oxygen. Protonation of the hydroxyl oxygen produces this intermediate. Protonation of the carbonyl oxygen produces this intermediate. This intermediate can be resonance stabilized. Therefore, it is more stabilized in the protonated form, and therefore this oxygen, the carbonyl oxygen, is the more basic of the two oxygens and is the one that we see protonated. Protonation of the carbonyl oxygen turns the carbon of the carbonyl group into a very good electrophile, which can then react with the alcohol. This produces a tetrahedral intermediate. Proton transfer from the ether to one of the alcohols leads to a tautomerization to this intermediate. The water that is formed leaves, and the carbonyl is reformed. In the final step, the water that's formed deprotonates the carbonyl to produce the ester product. An alternate method of synthesizing esters is very similar to the Fischer esterification, except it typically is more favorable. This synthesis reacts the alcohol with the acid chloride instead of the carboxylic acid. This produces the ester and hydrochloric acid. The mechanism for this reaction is similar to that of the Fischer esterification, except that it doesn't require treatment with strong acid and heat. Remember that the purpose of the strong acid in the Fischer esterification is to improve the electrophilicity of the carboxylic acid. The acid chloride is already a good electrophile because it has a good leaving group, the chloride. In the first step, the alcohol attacks the acid chloride to form the tetrahedral intermediate. In the next step, the carbonyl reforms, kicking off the chloride leaving group. In the final step, the ester is deprotonated to form the ester product and HCl gas, which can be removed from the reaction to help push the equilibrium to the right. Typically, the equilibrium is much more favorable for this alternate ester synthesis, and therefore we can obtain the esters in much higher yields.